This is a fantastic lesson that ties together a lot of algebra, from factoring and synthetic division to using the calculator to find x-intercepts, quadratic formula completing the square, and we're also going to be able to, looking at any polynomial, understand what's happening with the graph and its connection to the degree of the polynomial. Remember with factoring that you want to check in this order. To quickly review the sum and difference of cubes, you take the cube root of the first term, you take the cube root of the second term, remembering it's an odd root so the sign will stay the same, so that's why you see this staying negative. And then once you find the binomial, you square the first term, you take the opposite of their product, and then you square the last term. And because you're squaring, that's why that last term is always positive. And then you check for trinomial grouping. Let's get to the first example. It's all divisible by 4. I could do that now. That would be no problem, dividing both sides of the equation by 4. Or you could pull it out as part of the GCF. So that's one factoring technique. Always check for the GCF first. And now, because I have a product, I could use the zero product property, setting each of these equal to 0. But before I do that, I want to factor down this trinomial. So I have trinomial with a leading coefficient of 1. So I look just at the constant. And what is a pair of its factors that sum to the middle term's coefficient, the linear term's coefficient of 1. So that's going to be positive 3 and negative 2. Be very careful when working with 6 because it has so many factors, and if this was a 5, it could be tricky. So you always want to be careful with that one. So I rewrite this now in fully factored form. And of course, like 3 plus negative 2 is giving me that linear coefficient of positive 1. And 3 times negative 2 produces the constant of negative 6. So that was just regular trinomial factoring. With the zero product property, I'll now set each of these 3 factors equal to 0. And then solve for x. So here I divide both sides by 4, and I'll get x to the 4th is equal to 0. So what do you raise to the 4th power to get 0? Well, just 0. And then when you change sides, you'll change sides. And so I have found all of the roots of this polynomial equation. Don't write repeats more than once. So we have negative 3, 0, and 2. I like putting them in numerical order for readability. So just to talk a little bit, this one occurs 4 times because its degree was 4. Remember, the degree is talking about how many possible values can be in the variable. And then this one occurred once, this one occurred once, because their powers were each implied to be a 1. Looking at the next example, there are a couple ways to do this. First, you want to set it equal to 0 in anticipation of this step, using the zero product property to separate out the factors to solve them. So I got x to the 4th minus 26x squared plus 25 is equal to 0. Now, it's a trinomial. It has 3 terms, but it's a higher order polynomial of degree 4. So it's quartic. Now, I could just simply say, all right, it's a trinomial, set up 2 pairs of parentheses. I look at the factors of the constant. Since leading coefficient is 1, I could do that. So what are the factors of 25 that sum to negative 26? So it's going to be negative 25 and negative 1. And here's the deal. With the x to the fourth, I can't just put x and x here this time because their product is x squared. So instead, look at that middle term and realize that it is squared. That's often what is going to be in for the powers, because x squared times x squared is x to the fourth. Let me finish out this approach and I'll talk about something called use substitution, which you use in integration in calculus. So what I could also do here is say, hey, I have this x to the fourth minus 26x squared plus 25 is equal to 0. And because this term is squared of this term, so when you raise an exponent to an exponent, you multiply. So when this one is double this one, then it will factor. And I could say that u is equal to x squared. Now when I substitute that, I get u, and now it's squared because u to the fourth, like this, minus 26u plus 25, and now it's like a typical quadratic trinomial. So you would just say, okay, what are the factors of u squared, multiply together, and then negative 25 and negative 1 is equal to 0. And then once you get down to the next step, that's when you then substitute back in. You say, okay, u was actually x squared this whole time, etc., etc. So that is use substitution. Feel free to use it if it helps you. I'm going to continue using this approach here, and I set each of these factors equal to 0. Start solving for x by isolating it. Take the positive and negative square root of both sides. All right, so we have 4 distinct real roots, positive and negative 1, and positive and negative 5. Now let's look at this. Over here, in the previous example, the degree was 6. Of a polynomial, the degree equals the greatest degree among the individual monomial terms. So this one was 6, the degree of this monomial was 5, and of that one it's 4. So the highest among those is 6. Now, that means I have the potential for 6 answers, whether real or complex, whether unique or repeated. So here I have 3, but it's more than meets the eye because this one here, the 0, occurred 4 times. And then this 2 occurred once, and the negative 3 occurred once. So their sum is equal to the degree of 6. And then over here, I had 4 unique ones, which matches the degree. So keep that in mind. We'll come back to that when we talk about the fundamental theorem of algebra in the next lesson. So let's start pulling together the symbolic and how many times a factor occurs with what the graph looks like. So multiplicity is like the following. If I had, let's say, a number like 48, and I broke it down into its prime factorized form. So let's see here, 48 is 16 times 3, and then 16 is 4 times 4, 2 squared, 2 squared. Okay, so that's 2 to the 4th times 3. That would be the prime factorization of 48, where it's a product of primes using exponents for repeat factors. Now, the multiplicity of the 2, I would say, so it'd be like 2 with, sorry, I'm getting a little ahead of myself here. It would be 2 with multiplicity of 4, because that factor is there 4 times. And then I would say 3 with multiplicity of 1. Kind of using quotes so I don't have to rewrite that. That will translate in the same way to polynomials and their factors. So the multiplicity of a root is how many times it appears as a factor of the polynomial. So what I have here for us is the fully factored symbolic form of a higher order polynomial. When it's in this form, it's harder to see what the degree is because it's not written out like, let's see here, like this, etc. Because it's very easy in that form when it's all multiplied out to see what the degree is. But when it's in fully factored form, you have to think, if you were to expand this out, how many copies of x would you have? Well, right here you have 3 of these multiplied together, each containing a copy of x to the first power. So that would be 3 for the multiplicity of that factor, 2 for the multiplicity of that factor, and a multiplicity of 1 for that factor. So 3 plus 2 plus 1 means that the degree of this polynomial is equal to 6. It is essential that you find out what the degree of a polynomial is, because that will then tell you how many times a certain root occurs. If you're just looking at the graph, it's really easy to see here because you have both together, but that won't always be the case. So let's talk about a couple things with multiplicity. So even or odd is what I'm talking about with parity. Now, if it's even, let's think about where we've seen even before. That would be like a quadratic x squared. You get a graph that just kisses the x-axis at the point of intersection. Now, that's why when it's even, it's just going to touch the x-axis. So if you look at this example, I have here x plus 1 quantity squared. If I were to set that equal to 0, negative 1 is the actual root right here. And notice that the graph goes down, intersects at negative 1, and then comes back up. And that's because when you are squaring, you can't have any negative outputs, anything below the x-axis. So it needs to curve down and then back up. And then if you have an odd multiplicity greater than or equal to 3, you have the following result. It's only going to bend across the x-axis. And the reason for this, right here, I have x minus 4 to the third power, and if I set that equal to 0 and solve, I see that the root is 4 right here on the graph. Notice that it snakes through that point, because if you go back to cubic, remember that, well, if you raise a negative to an odd power, it's going to stay negative, and if you raise a positive to an odd power, it's going to stay positive. But what happens when you raise something to the first power? In that case, you need to think about that as a special case of odd. So here, it's going to linearly cross the x-axis. Because if you think about, just say, this example here, where that's the first power, if I solve that and set equal to 0, I should at 1/2 have an intersection where it kind of just shoots straight through. So it linearly, in a way, crosses the x-axis. It might have some curvature, but it's certainly not bendy like cubic, and it's definitely not reflective, so to speak, like even. And we could think about that just like a normal line. If you had the parent graph of a linear function, it would look very similar, just kind of going straight through. Now let's pretend for a moment that we did not have this fully factored form here, but we knew the degree, and we have this graph. Okay? By looking at how this curves, I know that it's an even root. And so that means it occurs an even number of times, 2 or greater. So 2, 4, all the way up to the degree of 6. I know it can't be a degree of 6 because it has to share with the other x-intercepts. So I look then at the next one, and you know what? Linear is the toughest because if you're not zoomed in enough, it might look like cubic. So I'll hold off on that one. I'll come over here, and this one bends through, so that's odd. So that can occur 3 or higher, so 3 or 5. But I can't go above the next odd number is 7, but the degree is 6, so that doesn't make sense to continue. And then this one is linear. So that means I know that it occurs once because it crosses straight through the x-axis. So now I need to kind of figure out the puzzle. What numbers add up to 6? So if I do 2 and 1 and 3, I get 6, so that might be a possible combination. If I do 4 and 1, I'm already at 5, so none of these will then work. So I can't do 4, and for that reason I can't do 6. And so it has to be 2, 1, and 3. And if you take a look, -1 here does occur twice. And then this one of a half is linear, it occurs once. And lastly, this one of +4 occurs 3 times. And that's how you have the multiplicities of each of the factors affecting the graph. The way you would present your answer then is by saying, okay, -1 with multiplicity (2), and then 1/2 with multiplicity of 1, and 4 with multiplicity of 3. And note that the multiplicities will always add up to the degree of 6. So in this example, you would not have this graph. So what you would do is put this higher order polynomial into the calculator, and it will look like this. And then from that graph, you're going to figure out what the roots are and their multiplicity, so how many times they occur as a factor. So this one looks pretty clear as a candidate for linear. It passes straight through the x-axis. This one seems pretty clear that it's bending through, so I'm thinking cubic or odd. So it could happen 5 times. And then this one is pretty clear that it's bouncing back, so I'm thinking even. So once I figure that out, I want to write that down below it. So this will be linear. And then this one would be odd. And then this one would be even. From here, well, linear can only occur once. Done. And please understand the following. We have a degree of the original polynomial as 6. It is the highest degree among the individual monomial terms. It's in standard form, so descending order of the exponents, so I know where to look, all the way to the left. So that's my amount of factors, multiplicity, that I have to give out to each of the roots. I can only trade 6. So linear is going to take 1, so I have 5 left. How can you split 5 between an odd and an even number? Well, 3 and 2. For even higher order polynomials, this gets a little more difficult, and you'll get opportunity to practice that in the homework. But in general, I would say 3, 5, 2, 4, 6. You go all the way up to the degree, and then you just see which works. So that's the combination that works. I would also check that. Oh, I'm already out. 1 and 5 makes 6, so then I wouldn't even have any left over for the even root. You'll pick it up through practice for sure. So I figure out how many times each occur, and then I write my answer. I have 1 linear root, and that occurred at -2. Now, if you're finding that on the calculator, you could just eyeball it. Go to a table. That will be easiest, though, because it's going to be really hard to put the left cursor here to find the intersection and then put the right cursor here to find the right side, the right bound, and then hit enter because this is such a steep curve. So that being said, I would go second graph for the table, verify that at -2 we have a 0 for a y value. So I have 1, so -2 with multiplicity of 1. And then here I have a root of 1 with multiplicity of 3. And lastly, I have that is a x-intercept of 4 with multiplicity of 2. And again, 1 plus 3 plus 2 is the degree of 6. So make sure the multiplicities always add up to the degree. Now, that's all this problem wanted, so that would be the answer. But now we would be able to rewrite this higher order polynomial in fully factored form. So I could say, let's say it was equal to f of x. So I have f of x is equal to, so I have a root, and I'm going to put them in descending order of the power. So I'll start with the highest one, which is here. That's positive 1. That's x equals 1. So then I need to set it equal to 0, so then they could multiply together and be equal to 0. I'm reversing what we were doing before with the zero product property. So I would say x minus 1 occurs as a factor thrice, and then here that's x equals 4, so then I switch signs, set it equals 0, so then x minus 4, it was an even root, it occurred twice, and then lastly I have the linear one, that's x equals -2, so then that's x plus 2, and that occurs once, so I won't write it. So that is the fully factored form of that higher order polynomial, and the multiplicities of how the shape of the graph like that, this bent, meant that that occurred twice. If I didn't know that, I wouldn't know how many times, what exponents to put on each of these factors. That's what multiplicity allows us to do. So now we're going to put all of this together. When finding all the roots, you're going to first go to a calculator, and then you're going to find the rational roots by finding the x-intercepts. And then, because there's a lot of work involved, we want to use synthetic division to then find the depressed polynomial after we remove that factor from the higher order polynomial. So we're trying to break it down into smaller and smaller pieces, distilling out what we already know. And then we'll solve the depressed polynomial by factoring or using the quadratic formula. So basically, you need to keep working through these steps until you get down to something that you can solve using these techniques. So maybe it's like at the beginning of the lesson where it's x to the 4th and might factor, or it'll be something that is quadratic, so has a degree of 2. So identify all real roots. What you need to do is you put that into your calculator, and from it, you'll find the following values, our x-intercepts. So step 1, you'll find that we have in the calculator 2 and negative 3/4 are x-intercepts. And then for step 2, I then need to synthetically divide those out. I need to remove those factors from the polynomial so then I can boil it down to find the remaining factors. Now, I don't want to work with fractions more than I have to, so that's why I'm going to start with positive 2 in synthetic division. Now that's x equals 2, so you do not change the sign. And then remember, you start with the highest power and then go down, grabbing the coefficients as you go, and you write a 0 if any of the powers are missing. Leave a little space. Bring down the first term, because you're adding it to nothing, because you always add down, and you multiply down and across, add down, multiply down and across, add down, multiply down and across, add down, multiply down and across, and we knew that was going to happen. A remainder of 0 from the remainder theorem tells us that 2 is a factor of that polynomial, which we found using graphical techniques, using a graphing calculator. So now, this is neat. What we have just found here is 4x cubed minus 13x squared minus 8x plus 3 equals 0. And we have boiled out the x minus 2 factor. But we want to continue breaking down this cubic because I can't factor that. I can't do the quadratic formula because it's not even quadratic. And so that's why I need to take a step back and keep working with what's called the depressed polynomial. The depressed polynomial is the one that results here from the division. And you could now apply the other factor that we found from the calculator, like so. Leave a little space, but now I don't want to put it all the way out here because this is a remainder of 0, so that's actually not even part of the polynomial. So I make it a little shorter because it only needs to go underneath that 3. So I add down, multiply down and across, add down, multiply down and across, add down, and finish up. Again, knowing I should get a remainder of 0, so I haven't made any arithmetic mistakes. That's a good check. And so now, because I've divided out 2 factors of x from a quartic polynomial, I have arrived at 4x squared minus 16x plus 4. And now that's equal to 0. And to show big picture what's going on here, when I did this division, I noted earlier that we would have this factored version of the polynomial. And then after doing the next synthetic division, we would have the following factored version of the polynomial. And so we have distilled down, we know this part, and now we're left with that quadratic. So if it factors, go for it. That's going to be the easiest way to get the answer. If you want to do completing the square, that's great too. But usually, I'll just go with the quadratic formula. So I substitute in. And in the interest of time, do some simplifying real quick. So this has factors of 48 and 3, and in 48 is a 16 and a 4. Rather, that's 64 and 3. And now, because every term in the numerator has a factor of 8 in it, so basically I could factor it out like this. That's why I could now divide out like this, because of that. And so I have found the remaining roots. So I would present my answer using roster notation. And I picked the 2 from before. And combine it with the ones that I found in the end by the quadratic formula. And let's count them up. I had a degree of 4 in the beginning. And then I have 4 here. This is 2 plus square root of 3 and 2 minus square root of 3. So they were all had multiplicity of 1.